We acknowledge the first Australians as the traditional custodians of the continent, whose culture is the oldest living culture in human history. We pay our respects to elders, past, present and emerging, and we respect their cultural heritage, beliefs and relationship with the land. We extend our respect to all Aboriginal and Torres Strait Islander people here today. They share the memories, traditions and hopes of the traditional ancestors with the new generations today and in the future. We would also like to thank them for looking after this land for thousands of years.
Jobs as well. So some of them have really cool toys like this drone that they can use to map in remote locations. Some people work in mapping hazards and understanding where they might occur. We have people that work in the lab doing different types of analysis. And we have people that even work with satellite data to understand the changes of Earth surfaces. So now we've told you a little bit about Geoscience Australia, we're going to tell you a little bit about us. So my name's Louise.
Hello everybody, my name is Joe.
And hello, I'm Lara.
And we all work in the Education Centre at Geoscience Australia. So that means that normally we are inviting school groups to visit us here in our building. But today, as you know, we're coming to you from Zoom. So as Karen said at the beginning, if you have questions for us, you just need to pop them in the Q&A box. Okay, so I've told you just a little bit about us. And before we get started today, we'd like to know a little bit about you and where you're coming to us from. So we have a poll for you, which will pop up on your screen in a moment. So if you have someone near the computer there that can answer for us, we would very much like to know if you are a student who's maybe learning from home today, so you're by yourself, you're an individual. We would like to know if you're a teacher that's got an entire class with them. And if you scroll down, you should see a second question asking you which state you are in. So we'll let those results roll in for a moment. We've got a lot of you with us here today, which is very exciting. And once we've got all those votes in, we will have a look and see where we've all come from. Fantastic. So it looks like we've got a lot of people learning from home. I can see the results rolling in. And that's a little bit like us too. Lara, Joe and I are all in different rooms by ourselves as well. We've got some people that are joining us with their class, which is very exciting. And looking at our results, most of you are coming to us from New South Wales. We've got some people from Victoria and some people from the ACT as well. Okay, so I think we're going to close that poll off now. Wonderful. And there's one more question we want to ask you before we start today. And that is about your experience with earthquakes. So we would like to know if you have ever experienced an earthquake. So hopefully you'll see that poll pop up in just a moment. Can everybody see that poll? I can't see it. There we go. Wonderful. So there's just 3 options for you there. So we'll try and get those in as quickly as possible. Okay, so I can see already that the vast majority of you have not experienced an earthquake. We've got some people that said yes, they've experienced one overseas. And we've actually got quite a few of you that say, yes, you've experienced one here in Australia. So this is very interesting. And I think that maybe if we asked you the same question a few weeks ago, that maybe the answer would be a bit different. So we're going to be talking a little bit about earthquakes in Australia today as well. Okay, so I think we're good to close off that poll. Most people have voted. Wonderful. Okay, so we're going to start off today by talking about hazards. So I'm going to hand over to Lara to tell you a little bit about those.
So we're going to be talking about earthquakes because that's what the title of our talk is all about. But let's just start thinking generally about hazards. So there are different types of natural hazards, and earthquakes are one of those. You might have learned about them at school. You might be learning about them now. What other natural hazards can you think of besides earthquakes? Maybe a couple of people might want to write something into the Q&A down the bottom. I can see the numbers going up. Joe, what sort of answers do we have there?
Oh, we are having so many flooding in. We have bushfires, we have tsunamis, we have cyclones, volcanoes. We've got some very smart people here. Oh, we've got floods now. Excellent. Wow.
Oh, they all sound very familiar. How about you share our list? And look at that. Look at the coincidence. All of our students have thought of the same ones that we have. Well done, everyone. So the next question then for you is the difference between a hazard and a disaster. So these are hazards that you've all thought of, earthquakes and cyclones and things. And these things happen, but they're only a disaster if someone or something gets damaged or gets hurt. So let's think about a hazard from around the house. So maybe some scissors. So if you have a pair of scissors in your hand, they're a hazard, but it's only a disaster with those scissors if you accidentally bump into somebody and hurt them, or if you accidentally maybe cut your fingers with them. Or a set of stairs. At my house, I have a very long set of concrete steps outside my house. And they're a hazard, they're only a disaster if I was to trip down them and hurt myself. And the same goes for these natural hazards. Now, there are actually two different classes or two different subgroups of natural hazards that we can make. So let's take some of that list and put them into two different columns. So we're going to talk about geo hazards and weather hazards. So geo hazards are ones to do with the ground, and weather hazards are to do with the atmosphere or the air and the weather. So we've got one that's come up. There's earthquakes. That makes sense. Earthquakes are the ground shaking, so we can put that one straight into that geo hazards column. So as we go through them, maybe you want to put your hands on your heads or shrug shoulders, hands on shoulders as we go through. What's the next one? Drought. So that one somebody mentioned in the Q&A. That's when we don't get rain for a long time. We get that a lot in Australia. So if the rain comes from the sky, therefore that's weather. That will go over to the right-hand side there. Volcanoes, somebody else mentioned that in the Q&A, didn't they? So volcanoes are when magma comes up as lava up from underneath the ground. So that would be a geohazard. Tornadoes, oh, that's those tight wind. We get them in Australia. We do also get them in the US, is where we're normally familiar with them. And because they're to do with the air, we'll put them over in the weather hazards. Cyclones, we get them in Queensland, don't we, and the northern parts of Australia in the tropics. They are massive storm systems. They can be 200 kilometres across. And because, again, they're in the weather, in the atmosphere, they'll go over to the right. Floods, we get them a lot too, don't we? When you get excess rain, the flood itself happens on the ground, but because it comes from the weather, then we'll put that over to the right. Landslides, so when the side of a mountain might collapse, that might often be caused by excess rain, loosening the material on the side of the mountain, but because it's on the ground, we'll call that a geohazard. How are you going, everyone? Are you getting these right? And tsunami, the last one on our list. So these are the big waves we get in the ocean. And normally waves are caused by the wind whipping up the water, but tsunami are actually caused by the ocean floor moving and shifting that water. And so because that's from the ground, if you like, the ground underneath the ocean, we'll put that in geohazards as well off to the left. Hope you got them right. So the next question then, because we've got earthquakes as our title I want you to do a quick brainstorm with the people in the room with you and have a quick discussion. What would you feel if you're in an earthquake? What would you see? What would you hear? So we're not after what is an earthquake, but more what would you feel, see, and hear? You've got 60 seconds. Okay, go. Right, time's up. I imagine there were some really interesting discussions at your end. Now, we have a lot of scientists that study earthquakes at Geoscience Australia, and their title would be a seismologist. And their definition of an earthquake is earthquakes are the vibrations in the ground caused by rocks breaking under stress. So if you imagine going outside and picking up a big stick and you put it under stress by trying to snap it, eventually it will break. And then the shaking that you feel coming from where it breaks down the stick into your arms would be the earthquake. And there's a nice diagram showing what that would be in 3 dimensions in the ground. You can see those circles there showing that shaking out. So what have you got behind you there, Louise?
Okay, so if you have a look now at the photo behind me, you will see that I have changed location. If you have visited us here at Geoscience Australia, you would have been into this room. This is our foyer. You go through it to get to the Education Centre, and has lots of cool things. You can see there's display cabinets behind me with lots of things in them. But I want you to look at the machine just to the side of me here. So you can probably see 2 white cylinders. So this is a machine that can detect earthquakes. So you just talked to Lara about what you might see, what you might feel, what you might hear during an earthquake. But this machine can pick up earthquakes that we can't see, feel or hear, and it's called a seismograph. So if we zoom in to have a closer look at this machine, we would see something like this. So we have these big cylinders, they have paper on them, we have to change the paper every day, and there's a pen that sits on top of the cylinder. The cylinder moves slowly and the pen draws a line on it. So you see most of the lines, well, all the lines on here are straight, except for these little notches in them. And the notches you see are just counting time. So this is what it looks like when no earthquakes are happening. So I'm going to give you just 10 seconds now to have a think about, maybe have a chat, someone else is in the room there with you, what the pen would do if an earthquake was detected. So you might be able to use your hand to show me how you think that pen would move. So I'll give you a few seconds. Okay, how did you go? So if you were doing something like this, you are correct. If that machine was to detect an earthquake, the pen would move backwards and forwards and it would give us a squiggle on the page. But for our seismograph to work, it has to be connected to another machine as well. And I've got one of those here to show you today. So this is called a seismometer. So this is the part that can actually detect and measure the earthquake. So if I take the lid off, we can have a look at the components inside it. So I'm going to ask you to be quiet for just a minute, and I'm going to be quiet, and we're just going to listen to what happens when I move this up and down. Are you ready? So hopefully you could hear that. So if you imagine that my movement was actually an earthquake that was moving this machine up and down, what you could hear was this little metal bit here moves up and down, and it taps the metal above and the metal below, and it makes a sound. So if this machine was plugged in and working, the sound signal, or that tap, would be converted to an electric signal. So we've got some electronics up the top there. It would pass through a cord or a cable to our seismograph, which is the part of the machine that can draw the earthquake. So we've got the seismometer to detect it, and we've got the seismograph to draw it. So we're going to have a look now at a video of what a seismograph would look like if it were an earthquake. So let's press play. So you see at the beginning it's drawing a straight line, then it starts to pick up some vibrations. That pen moves backwards and forwards, bigger vibrations give us bigger wiggles on our paper, and we get a drawing of our earthquake. I'll stop that one there. So if you were to come in one day to our building and there'd been an earthquake, you would see a squiggle on the paper. We would then take the paper off the drum. So because it is curled around, this paper, I'm going to have to get well away from the camera here to show you, is very, very long. So once we take it off, I'll turn it around. You can see here we had some straight lines, and then we had an earthquake happened, and you could see it was recorded as a squiggle on this page. So I know you can't see this very well, so we're going to look at some photos as well. So if we pop our photos up there. Here they come. Okay, so the first one we have is a photograph of our recording of an earthquake that happened in New Zealand in 2011. So this was a magnitude 6.3, which is not a huge earthquake, but it's quite a big earthquake. And because it happened really close to Christchurch, it was quite destructive. So even though we are very far away in Canberra from Christchurch, and we didn't see the earthquake or feel it, our machine was able to pick it up as a wiggle on the page like you see here. So the next earthquake I'm going to show you happened even further away. So it happened in Japan, which is almost 8,000 kilometres away from us, here in Canberra. So what do you think this might look like? It's very far away. So let's check it out. So this is how we recorded an earthquake that happened in Japan in 2011. And you can see it was a huge signal. This is because it was a very big earthquake. So this was a magnitude 9 that happened. And it was very strong, big vibrations detected even here in Canberra. And if we zoom out on that page, you would see not only were the vibrations very strong, but they lasted a long time. So the earthquake happened and the earth was actually vibrating for hours afterwards. So I've been using a word there to talk about these earthquakes. I've been saying magnitude. Maybe you know what magnitude is, or maybe you haven't heard of it before. So Lara is now going to tell us a little bit more about magnitude.
So magnitude is a word we can use to talk about the size of an earthquake, and it's actually talking about the amount of energy that's released by that earthquake. And you'll notice that when Louise has been mentioning numbers, they're anywhere between 0 and about 10-ish. So they're the sorts of numbers that we talk about when we're talking about earthquakes. And you'll notice that there's whole numbers and then point something. Now, I'm going to do an experiment here to think about the amount of energy in various magnitudes of earthquakes. And I'm going to start with a piece of spaghetti. So if we imagine that this is a single strand of spaghetti representing a magnitude 5 earthquake, then the amount of energy that's needed for me to break it is the amount of energy in a magnitude 5 earthquake. So you ready? Here we go. Oh, it's pretty easy. Okay, so magnitude 5, not too bad. Now, every time you go up the magnitude scale, though, you're going up by about 30 times in energy. So to go from a magnitude 5 to a magnitude 6, we have to multiply by 30 times in that energy. And so to do that, I can just get a bunch of 30 pieces of spaghetti and then break all of those at once. So you ready? Here we go. Oh, bits flying everywhere. That took a bit more energy. I had to put my thumbs in there and give it a bit of a push. So, okay, that was a magnitude 6. So that was 30 pieces of spaghetti. So to go up to a magnitude 7, I'd need 30 times 30 pieces of spaghetti. 30 times 30 is about 900. Oh, okay, here's a bunch. Here's a big bunch. All right. So that's compared to our bunch from before. So are we ready? We're going to break this one? No, I don't think even with my big muscles from going to the gym, I can break this one. So we'll just imagine that we break this one. That would take a lot more energy to snap that bunch compared to that previous bunch of 30. So that was a magnitude 7. Now I'm going to have to stand up because the next one, I'm going to use a piece of paper. So this would be a magnitude 8. So again, compare that to this. So we've imagined that this was all just one big bunch of spaghetti. That would be really big. Wow, I can't even get my hands around that. And then, wow. Step right back. This would be a magnitude 9. So if you imagine this is the ends of all the pieces of spaghetti, oh my goodness, there'd be nothing left in the supermarket. But if we then go back, magnitude 9 is this, magnitude 5. So small, can hardly even see it. There we go. Right, Louise.
Okay, so hopefully now you understand a little bit more what we mean when we say magnitude. So now that you know what magnitude are, we're going to watch a video and you're going to see some red circles appear on a map. Those red circles represent earthquakes. The bigger the circle, the bigger the magnitude of the earthquake. You'll also notice that when the circles disappear, they leave a little yellow dot so that we can see where all the earthquakes have happened for this year. So I'm going to press play and we'll talk a little bit more about the video as we go along. You'll also hear some clicks coming through. A louder click also represents a higher magnitude earthquake. And you'll notice at the bottom here, we've got the days ticking along. So first thing you might notice is that we get earthquakes happening on Earth every day, which surprises some people. I also want you to have a look at where we're seeing those earthquakes happen and see if you start to notice any patterns. Our yellow line here is a counter. It's just counting how many earthquakes have happened so far in the year 2011. And you can see it's already at over 1,000 by the time we get to February. So let's watch our video and see how many earthquakes we get in 2011. Wow, what happened there? If you miss it, we can rewind it and we'll have another little look, just in case you happen to look away from our screen for a second. We'll just have a quick rewatch of this. Have a quick chat to the person next to you if there's someone there with you. What do you think you just saw? Pause our video. So if you said you think we saw a really big earthquake, you are correct. That really big red circle represented the magnitude 9 earthquake that happened in Japan that we have already spoken about today. You already saw our recording here in Canberra from that earthquake. What you then saw afterwards was lots and lots of earthquakes happening afterwards. And we call these aftershocks. So they're not as big as the original earthquake, but there was hundreds that occurred afterwards. And if you look at our yellow line that was counting our earthquakes, you'll see it was roughly the same number of earthquakes every day. And then it suddenly went up very, very steeply when that big event occurred. So I'm going to fast forward our video now to the end of the year, just to save us some time. And you'll notice now that we've got lots of yellow dots on our map because lots of earthquakes have happened over 2011. If you could read the timer in the corner, you'd see it's over 9,000 for the year because now we're in December. So I'm going to ask you now to look at where we have lots of earthquakes and think about where we have no earthquakes or very few earthquakes and see if you see any patterns. I'm going to give you just a few seconds. If you're in front of your screen, you might actually want to try and trace this on your screen. I'm going to ask you if you can see any patterns as to where the yellow dots are. Could you play dot to dot with them maybe? Could you see any that link up? Just ignore the yellow line Because remember, that's our graph. That's not showing us where earthquakes happen. And just look at the dots. So I'll just give you a few seconds to do that now. Okay, so we'll come back to our picture of that map. So here's the map that you saw before. And maybe if you did your dot to dot, you would have drawn something that looked like this. Okay, so maybe you would have drawn lines like those to join it up. Do you have any ideas what you might have drawn there? Pop it in the Q&A if you like, or you can just tell the person next to you. If you have said something like tectonic plates, or even better, tectonic plate boundaries, you are on the right track. If you don't know what tectonic plates are, that's okay, because Lara is going to tell us a little more about them.
So to start with, I'm just going to show you an activity that you can download from our website where you can do, as it says here, get the finger right, do a puzzle. There we go. So this is a puzzle using the tectonic plates. And those are some of the shapes that you have just drawn or pretended to draw on that map. But of course, it still doesn't answer the question of what a tectonic plate is. So I've got a model behind me that I'm going to use to try and explain that. So shall I just tip that down just a smidgen? There we go. So you've probably recognized one of these. So a model, a globe of the Earth. And I'm going to take out a giant chunk through here so that we can see what is on the inside of the Earth. So the Earth is made of layers, and there are 4 different layers that we generally talk about. The outside layer that on this model is the thickness of a texture line on the inside here is what we call the crust. And it's like the crusty bit, like the outside of a piece of bread, in the sense that it's the more brittle part of the Earth. So this is the bit that we live on, and it covers the entire surface of the Earth. Then we've got this very thick orange bit, and this is what we call the mantle, and it's where the magma is. And if that material, that very, very hot rock from there, can manage to get out to the surface, then we call it lava. And then we've got 2 yellow layers there, the outer core and the inner core. They're too far away for our conversation today, so we'll leave them there. But this crust on the outside is very important, because it turns out that sometime in the long distant past, that crust broke up into giant chunks. And those chunks are still covering the entire surface of the Earth. There's no place on the Earth that doesn't have a chunk of this crust, but we call those chunks tectonic plates. And to give you an example, if we can find us, there we are. Here is the tectonic plate that contains Australia. So you can see that that would fit there. Can you see there's Australia? And there's our Australia on our flattened piece, and this would of course curve all the way around. It's not flat. So this therefore is our piece of crust, or our tectonic plate. And to give you an example of another one then, this one here is the Pacific plate, and they fit together like this. So you can imagine that these would fit together like this, and continuing all across the whole planet. Now this is a nice little model, but it's not really to scale. So I want you all to stand up with me. If you're standing up, arms out. So if you can get your arms out to about 1 meter, imagine that we've taken the entire Earth and we're holding it between our arms. So the Earth is about 1 meter in diameter. If the Earth was shrunk down to that size, then the thickness of the crust is about the thickness of your fingernail. So it's only very, very, very thin. It's not easy to make models like that to scale, but that is what is then moving around, and then those tectonic plates interacting on their edges is what then causes all these earthquakes we've been talking about. So if we're then saying that earthquakes are from the edges interacting, how do we get earthquakes in the middle of a plate like in Australia? Louise?
Okay, so to answer that question, we do have another video to show you. So this video was made very recently. So when we had an earthquake in Victoria not that long ago, one of our seismologists here at Geoscience Australia made the comment when asked how earthquakes happen in Australia. He said, because our tectonic plates are like a pavlova. So some of our friends in Western Australia decided to test this out. So this is a video from Oz Ed, and you can find it on YouTube. So they start off by cooking a pavlova. So if you have time, you can watch this video from the beginning and make your own pavlova and try it out. But we're going to see what happens just from when they take the pavlova out the oven. So let's hit play. Okay, so first thing we're going to notice, we've got our pavlova and we've drawn Australia in the middle of the pavlova. This is because, like Lara just told you, Australia is in the middle of a tectonic plate. And you know, we watched the video, we discovered that most earthquakes happen at the edges of tectonic plates. So how can we get an earthquake here in Australia? So that's what happened. Let's see what happens when we give our pavlova a little bit of a squeeze. And you can think of this squeeze as being like the tectonic plates bumping into each other or moving into each other. So let's have a watch. So gently squeeze the pavlova. So you can see the question at the bottom there. Being asked, where do the cracks first occur? So you can see the hands on the pavlova, and you'll notice the vast majority of the cracks are happening near the hands. So near the edge of the pavlova or the edge of the tectonic plate. But let's keep going with our squeezing. So maybe a squeeze happens from a slightly different direction. And we get cracks forming not only near the hands this time, we get them forming all the way through the pavlova, through to the middle there as well. So you can see if you keep applying pressure or stress, most of the cracks or most of the earthquakes happen at the edges, but occasionally that pressure or stress gets transferred to the middle of your tectonic plate or the middle of your pavlova, and we can get a crack or a rumble here in Australia as well. Okay, so I'll hand you back to Lara.
Thanks. So I have, of course, actually a picture behind me, but there, because you can see this person, where is he here? He's not actually moving. So this is a photo of the National Earthquakes Alert Centre, which is just a few meters away from where I'm sitting here at Geoscience Australia in Canberra. This here is Greg, and he's one of the duty seismologists. He's part of a team, and his job and his colleagues' jobs is to monitor earthquakes as they happen around the world. And they come in on these screens here. So all these screens, they're blue with lots and lots of lines on them. And each one of those lines is a bit like those scribbles that we saw on the piece of paper earlier of earthquakes being recorded on seismometers. So this is sent electronically through satellites and the internet straight into this control room here. And so his job and his colleagues' job is to monitor earthquakes, to understand what's going on in the tectonic plates, but also to do some tsunami warning, which happens as part of their role as well. So did you feel the earthquake that hit Victoria on the 22nd of September? So it was what we're calling the Rawson earthquake. It was a magnitude 5.9, and it was the largest earthquake to hit the southeast part of Australia since European settlement. And so one of the other jobs for our seismologists who work in that room and beyond is to populate things like this Earthquakes at GA webpage. And you can visit this one. So when that earthquake hit a couple of weeks ago, that right-hand corner thing, can you see it there where it says felt report? That was really busy. So when people were feeling that earthquake, they could ring in, they could write in and submit their reports of what they felt. So here we've got on the left-hand side, 5 different seismograms, so live data that was coming through to seismometers that Geoscience Australia operates. You can see it started off quite strong and then fades off over time, and you can see that the arrival times, the time that signal the signal was first detected at different machines is different depending on how far away they were from where the earthquake started. And that P that's been written there is what we call the primary wave. That's a marker that says this is where we first started to detect it. On the right-hand corner there, you can see a map of that part of Australia. And so there's a yellow circle in about the middle of Victoria. That's where the earthquake actually hit. And then beyond that, you can see there are colours spreading out, and those colours match the legend in the bottom left-hand corner. So if you look at the range of colours in that, you've got pale purpley blue right through to very dark red. We've only really used from the yellow off to the left. So they're the weaker, mid shaking off to weaker shaking. And you can see that that pattern then is the same from the earthquake, strong shaking in the middle and then weaker as you move further and further away. And that earthquake was felt all the way out to Adelaide, all the way down to Launceston in northern Tasmania, and all the way up to Newcastle in New South Wales. And because it was a magnitude 5.9, that's the size that's big enough to be detected by seismometers all the way in the US and Africa. So we've talked a lot about earthquakes, and we've talked about earthquakes, natural hazards versus disasters. So the last question then, just to sum up, can we prevent disasters? Well, when the ones that we've been talking about mostly of earthquakes, we can't prevent earthquakes, but we can do things to reduce how disastrous that particular hazard and some of the other hazards might be. So that top left-hand picture there, you can see an earthquake happening underneath a city. Some of those buildings are breaking and some of those buildings are just doing a little bit of a wobble. And so if we can build buildings to withstand earthquakes, that will prevent a disaster. We can have, like we showed you in that picture before, the tsunami warning systems. And so if there is an earthquake that could cause a tsunami, then we can send out warnings to that part of the coastline, and then people can go inland and uphill away from that wave. And if you're in the case of an earthquake, best thing to do is follow those things down the bottom right-hand corner. You drop, you go under a table for cover, and you hold on to that table leg until the earthquake is over. And if you'd like to practice that, later this month, there is the Great Shakeout, and there are instructions on that website so you can do a drill at home or in your classroom.
Okay, so I think we are almost out of time today. We've only got maybe 5 minutes left, but we do have time for maybe a question or two. If there's any questions in the chat, Joe, have you seen any that were particularly interesting?
I have. There has been so many questions come in from all these young scientists out there. And yeah, we had heaps. The first one I might pose to Lara was, what's the biggest earthquake we've ever had? And this came from a number of people, including Ivy and Isla.
So the biggest earthquake the Earth has ever had, that's ever been recorded, because of course we've only had the equipment to do these recordings for the last 100 years or so, was a magnitude 9.5, and that hit Chile in South America back in 1960.
Wow, 1960. So we did have a lot of people actually asking, is a magnitude 10 possible? I presume from your answer, no.
Well, when I get this question a lot, and I have asked our experts, and they say that if we wanted to have something beyond a magnitude 9.5 or so, we would need a bigger Earth.
A bigger Earth. Wow. Well, we've only got the Earth that we have, so we probably won't get that magnitude 10. That is good to know. Now, Louise, can our scientists actually predict earthquakes?
No, we're actually not very good at predicting earthquakes. So you saw from the video that we watched, we're quite good at predicting where they're going to happen because we know where those tectonic plate boundaries are. But we're not very good at predicting when they're going to happen or how big they're going to be. So one thing we can do though, and you saw our earthquake alert center a little bit earlier when Lara showed you that, is when an earthquake happens, we can then predict another disaster called tsunami. So we know that tsunami are caused by earthquakes, and the scientists here use what they know about the earthquake that has just happened to work out if there's a possibility we'll get a tsunami or not. So we're not very good at predicting earthquakes, but we are quite good at predicting tsunami.
And thank you to Isabella for that question. Now, Ethan asked a very, very interesting question about the movement of the tectonic plates. And they were wondering, does the angle of the movement of the plates actually change the type of earthquakes that we get? Do either of you want to tackle that one?
So it's about the relationship between the two. So if I put these two next to each other, can you see that there? So you can see we've got the two plates nestled into each other. Now this plate is moving northwards this plate is moving, I always get this wrong, moving westward. You've actually got a variety of different things happening on the edges there, depending on the rock type and depending on the density, so how heavy the rock is. So for instance, along this bit here, this up and down bit, that part is actually sinking underneath our tectonic plate and making a big trench on the ocean floor. But there are other things happening as things are moving northwards. And we've also got other things happening in New Zealand where you've got them moving side by side. So it's quite varied, but it's a very, very good question to ask. And by the time you get to year 9, you'll know all the answers because you'll learn about it at school.
Fantastic. That was a very good question and a very good answer, Lara, as well. So we are really running out of time now. There's a couple of things we want to tell you about before we go. So we'll just pop those up on the screen. The first one is, as Karen mentioned at the beginning, it is Earth Science Week, and we would like to wish you all a very happy Earth Science Week. We hope you've enjoyed our session today, and we hope that maybe you're joining for some of the other sessions later in the day as well. If you would like to see some more of Geoscience Australia's Earth Science Week, we've got events, we've got quizzes, we've got activities to do at home. You can check those all out on the URL that's on the slide or on the screen at the moment. And if you're a teacher in the room today, we also have the teacher professional development session that's happening this afternoon that you can join using this same link as well. So we just wanted to finish up by saying a big thank you to Virtual Excursions Australia and to Dart Learning for hosting us today. And of course, a big thank you to all of you for joining us from all over Australia.